Hi everyone. On behalf of the AI at UCI Club, I'll be presenting a video workshop on decision trees. For this topic, I want to answer the following. Number 1, on a high level, what is a decision tree? Number 2, how can I use decision trees to make predictions from a dataset? Number 3, what are the benefits of using decision trees? And finally, number 4, what are the drawbacks of using decision trees? Aside from a quick high-level summary, I will not go into precise detail about how decision trees are constructed, nor will I describe the mathematics behind the scenes. Instead, I'll talk about how to use decision trees from a programming standpoint. As programmers, we're often not interested in the implementation as much as the abstraction, since we can use someone else's implementation, but do note, understanding the implementation usually gives a better understanding of the abstraction. If you're interested in learning algorithmic and mathematical details of decision trees, there are many accessible and thorough videos on the topic here on YouTube. I will link a few of them in the description. Introductions out of the way, let's start with the first question. On a high level, what is a decision tree? The name decision tree accurately describes the underlying structure. Decision trees resemble the tree-like constructs found elsewhere in computer science, comprised of nodes, branches, and leaves. Within each internal node is a condition, and navigating the tree involves checking if each condition stored in the node is true or false for a given data point. This gives you a decision at each internal node. You take one branch if a condition is true, and the other if it is false. The aim here is to be able to predict something about a given data point once you have arrived at a leaf. Decision tree is said to be accurate when it can correctly label a sizable proportion of new data points that contain similar features to the dataset that it was trained on. Whether or not a decision tree is accurate lies with its construction, which is where most of the design nuance lies. Decision trees are recursively constructed from a dataset. This is done by separating data points into subsets based on differences in their features. For example, take this small dataset of colored rubber balls. Let's say, for each data point, we have a value representing the ball's level of bounciness, and a value representing the size. We can use these features to construct a very simple decision tree in an effort to predict the color of a ball, assuming there is any relationship between the features and the color we want to predict. To explore this example, let's plot a set of rubber balls on a 2D graph, like so. Let's try and intuitively separate the data points by drawing horizontal or vertical boundaries such that each group of data points becomes pure, with the fewest amount of boundaries drawn. We can manage this with only 3 boundaries. As you might have guessed, these boundaries are the conditions that you find inside of a decision tree. In this example, a decision tree that models this dataset might look like this. What if we add a data point to make one of these groupings impure? With the way this new data point is placed, it's still possible to make more boundaries so that we can keep our pure groupings. But is this something that improves the accuracy of our model? More than likely not, because, statistically speaking, our boundaries have significantly changed, even though we added only one new data point. Maybe this particular blue ball is an outlier because of non-standard air pressure, and most balls of this bounciness and size should be red instead of blue. When a model conforms so strictly to its training data that it lowers the overall accuracy, the model is said to be overfitting its training data. In the rubber balls example, the non-standard blue ball illustrated this idea, since most of the time, balls with those specified features should be red. However, because of the single outlier, balls with similar features will be classified as blue instead. On its own, decision trees have a tendency to overfit. Even with correct implementations that use Gini scores and pruning, which are meant to reduce this overfitting tendency, decision trees overfit more often than most other simple machine learning models. If you'd like to learn more about the Gini score and how algorithms can prune decision trees to make them more accurate, I've linked a few videos that explain the construction process of decision trees in a lot more detail. For now, I'll show how to use the Sci-Kit Learn implementation of decision trees in Python. Importing from sklearn, the tree module contains 2 types of decision tree classes, a decision tree classifier and a decision tree regressor. They handle classification and regression problems respectively, but using them involves calling the 2 same functions, fit and predict. After instantiating a decision tree, the fit function can be called to construct a decision tree model. This mutates the instantiated decision tree object so that it is ready to make predictions. There are two arguments that must be passed into the fit function. Seen here, the first argument, x, is an array of shape n samples, n features, where n samples represents the number of data points in the dataset, and n features represents the number of features of each data point. Referencing back to the rubber ball example, if we were to pass in that dataset to the fit function here, it would have a shape of 12, 2, 12 data points, each containing 2 features. The second argument, y, is an array of labels. These labels are the answers that the decision tree is meant to predict. Y corresponds to x. That is to say, the label in position 3 of array y is the label for the data point in position 3 in array x. After the fit function is run, the decision tree is ready to make predictions. The predict function accepts an array of features meant to describe a data point. This function returns a prediction of which label it thinks the data point should have, based on the data that it was fitted with. This same format of using fit and predict functions is used for most basic machine learning models in Sci-Kit Learn. Now that we know how to use Sci-Kit Learn's decision tree implementation, what sort of problems can we solve with it? This can be answered by figuring out what benefits and drawbacks decision trees have compared to other machine learning models. What are the benefits of decision trees? Decision trees are simple to understand, since, relatively speaking, there is less mathematics and data manipulation involved, and the premise of a decision tree is pretty intuitive. It looks and behaves like a flowchart. Decision trees are easy to visualize and interpret, even when trying to model complex datasets. When you're finished building a decision tree, you can always take a look through the various conditions that make the predictions, and, for whatever reason, you can manually modify it without much problem. Decision trees are also flexible. They can behave as classifiers or regressors. In addition, unlike other machine learning methods, you don't need to normalize your data to use a decision tree. Lastly, decision trees are efficient. They can process massive datasets within a realistic amount of time. These certainly seem like big benefits, especially if you know a thing or two about algorithmic analysis. So, what are the drawbacks? Decision trees are unstable. As we saw in the toy example with the rubber balls, a slightly different dataset could have a big impact on the form of the decision tree, and that impact is usually undesirable. In addition, there are many possible decision trees that can be built from a given dataset. Finding the optimal decision tree that best represents the data is a problem that is NP complete. That is to say, using algorithms as we understand it, it is impossible to find optimal decision trees within a reasonable amount of time as the datasets get larger and more complex. Instead, most algorithms find decision trees using greedy methods, which means immediately picking the best options as the tree is built without concern for long-term analysis. Finally, decision trees are relatively inaccurate when approximating real-world datasets. This is generally because of their tendency to overfit. These drawbacks mean that decision trees are not viable when trying to fit large, complex datasets. Since large, complex datasets are the kinds that we programmers most want to work with, this implies that decision trees are useless at first glance. However, this glaring weakness can be addressed using ensemble techniques such as boosting and bagging, making use of multiple decision trees to significantly reduce the tendency to overfit. For future learning with machine learning techniques related to decision trees, topics to search for include ensemble learning, random forests, and boosting.